Hello, my name is Trevor Smith. I'm the Business Development Manager here at Pico Technology, and I'm joined by my colleagues.
Anton Cholikov.
And Patricia Shalak.
And we'll be introducing in this video the PicoScope Automotive Ethernet Decoder Analyzer. So if you guys would like to take a seat for a couple of moments, we'll give a little introduction. So first of all, a little look back at what's gone on in the automotive industry over the past 2 or 3 decades. So back in the day when I first started driving my car, then each component in a vehicle, the brake pedal, had a little switch on it that triggered the rear lights to go on, or triggered the brake lights to go on when I pressed the pedal. That all changed in the 1980s when wiring looms in vehicles became too complex and too heavy. And we saw the first introduction of automotive networks. The original networks were point-to-point networks, so each node was connected to an adjacent node individually. It gave some improvements in terms of the weight and the complexity of the networks that were involved, but still not really perfect. The wiring looms were actually quite complicated back in those days, and there was no good standardization from one manufacturer's network to another. So as we moved into the 1990s, we saw the development of bus-based networks, and where each node was connected to a bus-type structure, and any node could be connected, or any ECU could be connected to any other ECU on the system. There were various different classes of networks, ranging from low-speed devices for convenience features, such as turning on the heater in a wing mirror or something like that, right the way through to much faster devices for functionality to do with the control of an engine. So looking at airspeed indication, rotation speeds, and feeding all of that into the engine control unit. So those networks developed quite strongly throughout the 1990s, and in particular there was one network that became dominant in the industry, and it was the CAN-based network. So CAN was developed in the mid-1980s, but became widely deployed in vehicles throughout the 1990s and beyond. Most vehicles on the roads these days have got some form of CAN-based networking in them, standardized by the ISO organization. And CAN is a 2-wire system. It's a differential bus. It has a CAN high and a CAN low signal. So CAN bus is immune in the presence of interference, which makes it a robust network for a wide variety of applications. More recently has been the evolution of CAN FD, CAN flexible data, which gives us up to 10 megabits per second data transmission, and with payloads in each packet of up to 64 bits. So CAN has served us quite well for a number of years. There are other standards that have commonly been used as supplements to the CAN bus architectures. So LIN is something that's popular for low speed sensor and actuator applications. The waveform that we're seeing on the screen here is a CENT bus waveform. CENT is single-ended nibble transmission. It transmits 4 bits of information with each edge there, and it is used extensively in sensors to do with engine and management and position control. So throttle position indicators, mass airflow sensors, temperature information that's being transferred typically to the engine control unit. And the majority of vehicles on the road these days are a mix of CAN and one or more of these other networks. So those architectures, that mix of architectures, has served the industry rather well for 10 or 20 years. But there's a fresh set of expectations and demands that, that we as users and drivers of these vehicles are expecting. So the next generation of vehicles really will become, in effect, mobile data sensors, and they will process huge amounts of information. So there are all sorts of sensors to detect proximity to obstacles and other vehicles and that sort of thing. So there's a whole range of driver assistance aids that are being deployed in vehicles now that use cameras, radar, LiDAR and other sorts of sensors. So there is a big move to, and particularly as we go towards the adoption of autonomous vehicles, there will be a huge increase in the amount of data that these vehicles will be using and processing. So the industry needs to adopt needs to find and adopt a new standard. And of course it's fairly widely reported that the standard of choice that the industry is clustering around now is the BroadR-Reach Automotive Ethernet. It's a standard that's been adopted by the IEEE as the 100 base T1 standard, commonly known as, and it is something that is promoted by the Open Alliance BroadR-Reach physical layer transceiver specification. The beauty of BroadR-Reach is that it is a form of Ethernet that takes advantage of the widespread use of Ethernet technologies that are already around in non-automotive applications. So the idea of BroadR-Reach is that it takes existing Ethernet technologies but puts them into an automotive environment, and in particular what's needed is to get rather than the multi-cable looms that the car manufacturers, the vehicle manufacturers are trying to avoid, is that it transmits data over a single unshielded twisted pair copper cable. So in fact this is kind of how the communications network looks like between two transceivers. So for instance a master on the left and a slave on the right. So the section over here would be a traditional Ethernet hardware on both sides in fact, but the PHY, the physical layer implementation of BroadR-Reach, takes us to a world where we have just a two twisted pair wire that's transmitting the information of the Ethernet. So gone are the days where we had a Cat5 cable with different strands of copper cable in there, some transmitting, some receiving. That's not the way that the BroadR-Reach Automotive Ethernet is implemented. Instead, really, what we have is just a simple single unshielded twisted copper pair of wires to transmit the data from transceiver to transceiver in the Ethernet system. So that gives rise to certain problems when it comes to testing and integrating a working system, because the MAC and the PHY device will typically be implemented on the same chip. So if we want to observe and see what is the information that is being transmitted in both directions, then we've got no way of probing inside that section of the device. So the probing points that we have really are at the master and the slave devices, rather than inside the Ethernet devices further down the system. So that introduces one or two problems and some challenges from a test engineering point of view and a design verification point of view that we needed to address with the PicoScope BroadR-Reach decoder and analyzer. So at that point, I'll I'll hand over to Anton to take us through the decoding mechanism.
Thank you very much, Trevor. Now, as you mentioned, there are a few challenges that are presented with decoding Automotive Ethernet, but let's first understand the signal that we're looking at. Automotive Ethernet uses PAM3 data encoding for each of the unidirectional components from master to slave, or conversely from slave to master. PAM3 means that the signal is composed of three-level symbols. So each symbol can be -1, 0, or +1 volts. And each pair of ternary symbols is going to encode 3 bits of information. So there are 9 possibilities for the states of 2 ternary symbols. We're going to not use one of those possible states, and we'll be left with 8 possibilities which can encode 3 bits of data. And in turn, we're going to slice up the parallel data going between the Mac and the Phi chips into 3-bit chunks and encode them via this PAM3 encoding. So the unidirectional components of this PAM3 signal from each transceiver to the other are going to interfere across the channel, and you're actually going to end up with a waveform that looks a bit like this if you probe somewhere along the channel. This presents a challenge because if you are a transceiver on the channel, you know your own contribution to this signal, and you can subtract it and infer what the other party is trying to tell you. However, if you are just a passive listener, you aren't able to figure this out and subtract that contribution. Therefore, we had to develop a technique to separate out the directional components. And in practice, out there are solutions to this problem that involve inserting a hardware directional coupler in the link. But these solutions are costly, and they're also very intrusive because they change the characteristics of the channel. We realized that there is an alternative here. By probing at 2 different points along the channel, we can use frequency domain analysis to work out which components of the waveform are traveling in each direction. So this directional coupler feature is presented in the form of a typical map channel in PicoScope, albeit with a few more parameters than usual. So in order to define a directional coupler, which is going to extract out the signal going from probe point on channel A to probe point on channel G, we also have to specify the cable length, the cable type, and the cable length, because we use the velocity of propagation in the particular cable type and also the separation between the probe points in order to do our analysis. And given this information, we're able to go to the frequency domain, as I said, work out which component is going in which direction, and reconstruct the directional signals. And I should also point out that getting the signal in the opposite direction, so from point D to point A, all you have to do is reverse these arguments. So after you've done this, you will get a PAM3 signal and the separated waveforms going from master to slave or slave to master along the same channel can be extracted. Then they can be decoded using our BroadR-Reach decoder, which my colleague Patricia is going to tell you a bit more about.
Thank you, Anton. So as Anton said, we also provided the decoder for you, BroadR-Reach decoder. If you haven't used before any of our decoders from our decoders palette, in order to set up a decoder, which is for instance BroadR-Reach one, you go to Tools from the top ribbon and you select a serial decoding option. And it should pop up a dialog, which you can, by pressing Create, from the display list, you can select the one that you're interested in, which for instance in now would be like BroadR-Reach. And by clicking this, it should also bring up a settings dialog, which is required for further setup of the decoder in order to decode the data correctly. So the first part specifies the signal, which would be the decoupled math channel signal. Further, there are configurations, which are, if you don't do anything, it should calculate it for you. But if you want to tweak it even more, there's a high threshold and low threshold that defines a high value of the digital level, which is 1, and middle, which is 0, and below the low level would be -1. So that's your PAM3 digital beats. And also you need to specify whether the decoded signal is a master signal or a slave signal, because they are using a slightly different scrambling technique. So that would give a hint to the decoder algorithm which one to use. So this is a basic packet, BroadR-Reach packet that was decoded from the data behind it. As you can see, the very beginning is what is called preamble, which is kind of a synchronization, like handshake synchronization pattern for both master and slave, or transceiver to transceiver synchronization route, which at the very beginning, when the pin, which is called TX enabled, goes high, it inserts 6 consecutive zeros, which indicate the beginning of the packet, beginning of the transmission. So the BroadR-Reach decoder decodes the packet, which contains the information about MAC address of the source, MAC address of the destination, also some payload, ether type, which also defines VLAN information, etc., etc. And in the end, there is a CRC, 4-byte CRC definition or information, which is validating the packet, whether it was sent correctly or not. So that's basically it. You have additional features like you can select which fields to present or not, depending on which information you're interested in, by selecting View Fields, or you can adjust the font depending on your preferences. Also, you can filter packets that you're interested in depending on the column, so depending on the type of information you know. And as you filter out the information that you have, you record it, you can also search through different kind of information. Like for instance, in here we've got ether type that we are interested only in this value showed here, and you can, by clicking these arrows back and forth, you can navigate through your filtered table. So that's basically it. Back to Trevor.
Thank you, Patty. So we'd just like to finish off by saying what are the hardware requirements for the BroadR-Reach decoder analyzer. And actually they're pretty simple. The only hardware that you need is a PicoScope 6000. Any model in the range from 250 megahertz up to the 500 megahertz models. So take your pick of those, and you need 2 of the TA045 differential probes, one each for measuring each end of the test points on the BroadR-Reach network that we looked at before. So if you're lucky enough already to have a PicoScope 6000 and the differential probes, then there is no additional investment required at all to start looking at your BroadR-Reach communications. So we'd like to finish then just to say that the BroadR-Reach analyzer decoder now is included as standard with the latest version of PicoScope 6 software that is available free of charge for download from our website. And if you do have any additional questions, then we've written a little section on the A to Z of PicoScope on our website, and you can find that at www.picotech.com, and then downloads, or you can go into the A to Z section to see a little bit more information about the material that Anton and Patty have just presented. Thank you.